Graphing exponential functions. So first of all, graphing exponential functions, what we graph is not going to make a line because this is not a linear function. So if you take a look here at what we have kind of have 4 different examples of what the graph will begin to look like. So on the left over here, we have one scenario. And in this scenario, first of all, I want you to focus on kind of this blue part that's going up. Now, when the blue part kind of goes up like this, that is when your B value is more than 1, and we tend to start looking at that as kind of like a growth, okay, which we'll hit on more later, but your function is essentially growing. So your B value is 2, 3, 4, bigger than 1. Now, the red graph we get still when B is greater than 1, but when we take that A value and we make it negative. So if A is negative, or down here less than 0, essentially what it's going to do is it's going to reflect it over the x-axis. Now, over here on the right, we kind of have the opposite version of that, and this one isn't growing. If you follow it, it's kind of like going down. When it's going down, we start using the word decay. Okay, if you're talking about science class, there's kind of like exponential decay, but going down. And that's when your B value is between 0 and 1. So 1/2, 1/4, 0.25, a decimal, or a fraction. Then when you take your A value and make it negative, you take that same graph that kind of has your going down or your decay, and you reflect it over the x-axis. Now, there's something else going on in all 4 of these that we're going to take a look at before we actually go to our next example. And in order to do that, I want to consider the function y equals 0.5 to the x power. So essentially our common ratio here is going to be 1/2 or 0.5. So each time we're going to multiply our function by 1/2. In order to graph this and start to get a look at what it's going to look like, we're going to make a table, x, y. And in our table, let's put -2, -1, 0, 1, 2, 3, 4, and we'll just call that good for now. Then I'm going to go over here. Let's go -1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Do the same thing. And let's see what happens. Okay, so first of all, I'm going to substitute in -2. So we're going to have 0.5 to the -2 power. Grab your calculator. And then we're going to get 4. So we know on our graph, we're going to go -2 and then up 4. Now we're going to substitute in -1. So 0.5 to the -1, which is going to give us 2. So -1, 2. Then we're going to substitute in 0, which is going to give us 1. Then I'm going to substitute in 1, which is going to give us 1/2 or 0.5, which is about halfway right there. Okay, and now where we're going to start getting interesting. So 0.5 squared is going to give me 0.25, which is about 1/4, which is even smaller. Then I'm going to substitute in 0.5 to the third. At this point, I'm going to grab my calculator again, which is going to give me 0.125, which is still little, but littler. And then let's just do this one more time, which is going to give us 0.0625. And now we need to stop, which is even smaller, and have a conversation. Okay? Picture yourself standing looking at a wall. Okay, you can do this in your house. Go to a wall, stand 10 feet away from the wall. Then I'm going to ask you to cut that distance in half. So you're at 10 feet. You cut that in half. Now you're at 5 feet. Well, you're 5 feet away from the wall. Cut that in half. Now you're at 2.5 feet. Well, cut that in half. Now you're at 1 1/4 foot. So the idea here is you're cutting it in half and in half and in half, and it's getting smaller and smaller and smaller. But if you have a number and you keep cutting it in half, will you ever technically get to 0? And the answer to that question is no. You're going to get really, 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 really small. But technically, if you have something and you cut it in half, you never take all of it away. So if I look at this function, it goes 4, 2, 1, 1/2, 1/4, 1/8, 1/16. It's getting smaller and smaller and smaller, but it's never going to reach 0 because I just keep taking half. This idea, and this is 0, so I'm going to draw a line here because it's never going to get there. Okay, this idea of getting smaller and smaller and smaller and getting closer and closer and closer, but never actually getting there, is called a horizontal asymptote. Okay, and a horizontal asymptote is a line that the function approaches and gets really, really, really close to, but never actually touches. So when we graph this, we're going to graph it, and this one's going down, it's decay, and you're going to come and you're going to get really, really close to that pink dotted line, but I don't want you to actually touch it, okay, even though your dots are getting so small that you can barely even see them anymore, because it's just a half and a half and a half. So if we go back up and we look at our 4 examples up here, there's a horizontal asymptote at 0 that both of these get so close to but never touch, and another horizontal asymptote at 0 that both of those get really, really close to but never ever touch. And again, that word is asymptote, which is a line that it gets really close to but never touches.